Sir, how can we express the potential energy of a system which is under one electric field E?
Which question?
I think 7B.
Second homework.
Second one, yeah, correct.
Next one. Seven B is it? Yeah. See, if this external electric field is not there, then what is the potential energy?
It'll be K Q1 Q2 by R.
But
R1.
there is only external electric field and there is only single charge. Okay. What is the energy required to build the system?
Electric field into displacement from infinity to that point.
Okay, that's one way to look at it. Or you can say, because of the external electric field, there will be potential at all the points, right?
Yes, sir.
Hold on. I'll explain. See, there is an external electric field. External electric. If there is some external electric field, okay? It is there in all the points in space, right? In general. Okay. So
yes,
because
sir.
of electric field, all points will be a potential, some value.
Yes, sir.
Okay. So if you have to bring this point charge to this particular point, say point A, and let the potential at that point be VA. Okay. So the work done to bring Q1 from infinity to this point is
Q1 VA.
Because potential at this infinity point is 0. Okay.
Yeah.
Now, if you want to bring the second charge, say to point B, okay. So at this point, there will be a potential to external electric field. Let me call it VB due to the external electric field plus the potential at this point B due to this point charge at let me call it VB due to Q1.
Yes, sir. So we have to specifically mention that, like, at that point there is a potential VA due to electric field. Okay.
Yeah, VB due to the electric field plus this potential to this point charge Q1 will be KQ1 by this distance R12. R12 is or RAB is the distance between A and B. Okay, so this is there in NCERT book. Let me just open it.
I thought we have to just express it directly by using the electric field E itself.
See, what is changing in external electric field? Okay, due to single charge. Okay, so V of R is a potential due to the external electric field at the point R. So I'm moving a point charge Q from infinity to the point R. Okay, so the work done is Q to VR. Right? Is that clear?
Yes, sir.
Okay, now we have two charges. And there is an external field. Okay, so the work done to bring the first charge, which I can take it as Q2. First, I'm bringing Q2. Hold on, let me not get confused. No, first charge is 1 only. So the work done to bring Q1 is Q1 into potential at the point R1. Right? There's no other charge. When I'm bringing the second charge, so potential at point 2 will be VR to the external electric field plus the potential at the point 2 due to this Q1. That is Q1 by R12. Is that clear?
Sir.
Okay, so the extra terms are these two because the external electric field. First two terms are due to the external electric field, due to the interaction between 1 and 2. Okay.
Yes, sir.
Any other question?
So for negative resistance, it's possible for galvanic cells, right?
See, negative resistance means we can understand resistance as the slope of the curve, right?
Yes, sir.
V is the independent variable, I is the dependent variable. So as voltage increase, the current will increase, and usually be a zero current when the voltage is zero. So this is the slope is what? 1 by R. Okay. So this is a positive slope, but suppose the IV characteristic is going like this. Okay. So this part, the slope is negative. Okay. So that means R is negative. So basically, resistance positive means as V increases, I will increase. But it's also possible that V increases, the current should decrease, and the current will decrease. This is negative resistance. It is possible in certain devices. I think it is there in the basically in semiconductors.
Sorry, sir.
Yes, no, I'll show. Third chapter, if you put negative. Let's see deviations from Ohm's law. See, this is a diode. Okay. You might read a little bit later in gold standard. Here, even though it's not a straight line, as long as voltage is increasing, current is increasing. So it's always positive resistance for all the points here. Even here also. Okay. But here, especially semiconductor gallium arsenide, it's possible that up to here it's increasing. As you increase the voltage, the current is increasing. But beyond this point, when voltage is increasing, the current is decreasing. So there's negative resistance. Okay. Because there will be two factors which is determining the resistance. So as voltage is increasing, the second factor is dominating. So as voltage increases, the current will decrease due to certain reasons. Okay. But there is some other factor which is there, because of which the current will decrease as the voltage increases. And in this region, that factor is dominant. So it becomes like the current will decrease as the voltage is increasing. And after that, still that's again positive resistance. And there's a nonlinear region because it's not a straight line, it's a curve. Okay, this part is linear, straight line. As voltage increases, current increases as a straight line. But here it increases, but not as a straight line, but as a curve. And after this, saturation decreases. Okay, this is part of limitations of Ohm's law. Because Ohm's law states that as V is proportional to I, but even in general conductor, there will be small deviation. Like as voltage increase, the current will not increase that much. After some time, there will be saturation. Okay, so this
Yes, sir.
deviation is the so we can say Ohm's law is valid up to this point. Beyond this thing, non-linear effect comes in. So you can see the resistance is uniform from here to here, right? But when the current flows too much, temperature will increase, so resistance will increase. So the slope has to increase. So that's what is happening here. Here the slope is increasing. Here the slope is resistance because V is in the y-axis. So here the slope is some value, after that increasing, and here it becomes infinite. Okay, because as current flows, it will get heated up, so resistance will go up. So it is matching with that understanding. Resistance will increase as the, or I should say, resistance will increase as the temperature increases. And since the current starts flowing, the temperature will increase. So once the temperature increases, the resistance will increase. So the current will not increase that much. This clear?
Yes, sir.
Diode.
Sir, what? Like I wrote it like my one understanding was that if I increase the I, the potential will start decreasing. or with respect to I?
Actually, voltage is independent variable. So, see, I you cannot increase beyond a certain point, right? This is the peak value of I.
Oh, yeah, correct.
Okay. So, what is under your control?
So like for when you're charging a cell, right, it's
Yeah.
actually inverse, right?
Charging is like pushing the charge into it. Okay.
Yeah, because like we're
Applying
pushing charges into negative electrode.
yeah.
So technically, can we say like current is opposite to the voltage?
Obviously, the circuit diagram, no. But talk about the electrochemical cell.
Yeah, like that.
Yeah.
Like naturally, current should flow from high potential to low potential, but here we are applying a third force, like an extra.
That is different, man. That is charging current. Here it's like a
I said,
device which is consuming power, no. So there it is opposite. Uh, this is more. This is like a passive device where I'm supplying voltage and uh, driving current to the. That's a different thing. Charging is a different. Oh, this is what I had in mind with that question. Like Ohm's law is not strictly valid, that is one point. And second is may not be a straight line, it can be much more crazy using a semiconductor because there are different phenomena which are acting to give this VA characteristics. And for semiconductor like gallium arsenide, it's also possible for the current to decrease as the voltage increases. So this is negative resistance. So other things you can do.
yes, sir. It was possible.
What about this one?
When the length of the conductor is 1 meter, and then the cross section area it's one meter square.
Also, length can be 2 meters and cross section area can be 2 meters square. Okay.
Yes, sir.
Basically, L by A should be 1.
Cell constant.
L by A should be 1. So if L is 4.5 meters, area should be 4.5 meters square. Okay.
So this L by A some physical quantity. Is there any quantity here?
Yes, geometry, no? It's a proper conductor. So whatever is the conductor, it can be of any shape. So the cross section can be also like this. It will not be a perfect reverse shape. But it should be uniform. If the area here is A, so the area should be A. That should not change. Okay. And let this length be L. For this conductor also, the resistances are equal to rho into L by U. So this formula is not valid for a conductor like this. Small area, here is a big area. This I cannot appear here, no? Because I don't know what is A. Here it is A1, here it is A2.
Yes, sir. Makes sense.
For this, if you want to find the resistance, I take a small element here, where area is approximately constant A, and the length is dl. So find dr of this particular length, dr, and if you integrate dr, I'll get total resistance R. Okay, this is the standard problem. We have a sort of a conical wire with a area cross section from A1 to A2. I can find the resistance of this thing in terms of the resistance of the material rho and L, and then A1 and A2. The resistance will be a function of L, A1, A2, and resistivity rho of the material. Okay.
Yes, sir. Sir, how far did the class go, sir? On those 3 days?
Just a minute, someone is chatting. Who's Pushpanjali? What is the question?
Sir, those last 3 days, right? What happened, sir?
Which 3 days?
The last 3 days, sir. before school was on vacation.
Didn't understand.
Sir, before school closing, the last 3 days, sir.
Yeah.
Like what happened, sir?
What happened mean?
In physics, or like till what it was taught?
No. Come again.
So till where are we, sir, in physics?
You mean the portion?
Yeah.
No, you are not in class.
Yes, sir.
Yeah. I just come up to Ohm's law, right? So I said in the this someone has joined. Wait. Mohita and Pushpanjali. Okay. Yeah, basically I covered up to this one, right? Yeah, I think you were there for Ohm's law, right? When I covered Ohm's law. Yeah, only
I
up,
was there until equivalence of Ohm's law.
yeah, only up to that. Yeah, after that I did some this drift velocity and yeah, this one. Drift velocity becomes and this did you read or not? This thing.
Yes, sir, I read that.
Okay. Okay. Mohita, can you hear me? Unmute your mic. Who is Pushpanjali? Any idea? Tarun?
No, sir.
Okay. Mohita, unmute your mic. Okay, let her unmute. I don't know what she's doing. Yeah, I think I set up the Ohm's law. So Ohm's law means I shall set up the drift this one. Okay, it's up to 3.5. See, this is a conductor, right? For example, it can be a metallic conductor. So there will be free electrons in this inside this one because it's a conductor, right? The valence electron, the outermost electron is free. So the free electron will move because of the electric field. Okay, since it's an electron, it's negatively charged, right? So it will move opposite the direction of the electric field. So the electron will move from left to right. The arrow is shown here. Okay, so this motion of the electron with this electric field is drift velocity. Okay, in addition to that, because the temperature, the electrons will move random.
Yes, sir.
Okay, so that random motion is because the temperature is called thermal velocity or random velocity. So this motion is random, right? Like it's actually the electron is going from here to this place. It's hitting an atom. It's like a collision. So it'll change the direction. Again, hitting an atom, change direction. So it's a random motion. In top of that, there is a drift in the direction from B to B prime. So B prime is because the electric field is present. Straight and travel is between the positions. Okay. If an electric field is applied as shown, the electron inside the B prime. Okay. So because the electric field, the electron will move in the direction opposite the electric field, which is towards right. So if the electric field is towards left, so the electron will move towards the right towards the electric field. So if electric field is not there, the electron will follow this blue line and end up in B. Because the electric field just follows the dotted line, so it landed in B prime. So this displacement B prime is the drift motion. So the current is because of the drift motion. Because it's random motion, it's finally, if you wait for sufficient amount of time, this B will go here and come back, finally come back to A. Okay. Or it can come somewhere here on the left side. But because electric field move towards right, so there will be a net drift of electron motion towards right. So this drift motion is the one which will give the current. Because if we take a cross section area here, what is the charge crossing towards right? That is due to this motion, the drift motion. Because it's random motion, once it will cross towards right, after some it will cross towards left. So net motion is 0. So only the drift motion is contributing to the motion towards right. That'll give rise to the current. Understood?
Yes, sir.
Okay, but another interesting thing is this random motion velocity or the speed and the drift speed. This random motion speed is much higher because the random motion is this much of distance, right? So much of distance is covering in that much time, but the drift motion is covering only this much distance in the same amount of time. So the drift velocity is much smaller compared to the random velocity. There is an example here. See, compare the drift speed with thermal speed, that is the random speed. Okay, so they run some calculation. They call the drift speed as 1.1 mm per second. So in 1 second, it covers distance of 1.1 mm. But the thermal speed is how much? 200 meters per second. It's traveling a distance of 200 meters, and the drift speed is 1.1 mm. So you can see the difference, right? So even though thermal speed is very high, it's useless because its direction is not fixed. It's changing direction. So effectively, it does not move. Like you're moving towards right 10 meters and then moving towards left 10 meters. Effectively, you're not moving anything, right? So this motion is like that. It's random direction. It's not in a particular direction. This in a particular direction for electron will be opposite to the direction of the electric field. So this motion will give rise to the current. This will not give rise to current. And this velocity can get by comparing the thermal energy. Thermal energy is 3/2 kT. This is actually 11th standard, the last chapter, standard theory of gases. In that, temperature will correspond to some energy. So that energy is 3/2 kT. That's basically the kinetic of the microscopic motion. This V is thermal motion, random velocity. Okay, so from
So
this,
can you explain that a bit, sir? The thermal energy concept alone.
yeah, this basically given by Boltzmann. So, what should I say? Yeah, if your body is at a temperature T, then the microscopic yeah, this is like a single electron, right? So the mass here will get a kinetic energy of half m v square, which will be equal to 3/2 kT. Okay, so since this moving mass is an electron, so if you put the mass of the electron here, you get the velocity of the electron. See, when if the body is at a particular temperature T, this K is a constant, Kb, Boltzmann constant. It's a universal constant. Okay, that value is fixed. So once a temperature is of a body is T, then anything which is moving inside will have a kinetic energy half mv square. That will be equal to 3/2 kT. So suppose an ion is moving. So I have to put the mass of the ion here. I'll get the velocity of the ion. Suppose an electron is moving, I have to put the mass of the electron and get the velocity of the electron. But since it's a solid, the only thing that's moving is the electron. So I have to put the mass of the electron and get the velocity of the electron. But suppose you take the electrolytic solution, and if it's a temperature T, they're both ions and positive ions and negative ions are moving, right? So if you put the mass of the positive ion, I get its corresponding velocity. If you put the mass of the negative ion, I'll get the corresponding velocity of the negative ion. Okay. So in some sense, if I have a body of a temperature, everything inside if it is moving, kinetic of any of them will be equal to 3/2 kT. So from that, I can get the velocity of the individual particle or whatever is moving. Okay. So you have to unmute your mic, Muita, Pushpanjali, to say if you have any doubts and what about your homework, how much you have done. Unmute your mic. What is unmuting? Okay, anything else? Tarun. So go with the example. This is the basic idea. Once you know the temperature, I can get the energy of any particles moving inside. That'll have energy of T by 2 PT.
Yes, sir. I got it.
Okay, and so I can relate the current to the drift velocity. First, I can get the drift velocity. Okay, I think certain things have been removed. This is, I think, the latest question of the book. One formula is missing here. So you got your textbook, no? This is the relation. I equal to, yeah. With this relation, it gives me current. So I have to relate the current flowing in a conductor to the drift velocity of the electron. So, okay, E is the electron charge, N is the number density of electrons, number of electrons per unit volume. Okay, so the way to remember this formula is V now. So one E is not there, so it's V, E, N, A. V is the drift velocity, is the electron charge, N is number density of electrons, and A is the area of the conductor. The area of the conductor. Okay, so for copper atom, okay, density is known, right? Once you know the density, I can know number of copper atoms per unit volume. Is that possible? Because mass of each atom I know. It's atomic mass. That is 63 point whatever. Okay. So from this I can find N. Another thing is N is same as number of free electrons per unit volume. Why is this true? Why is it true, Tarun? capital M is number density of copper atoms. Okay, that is same as number density of free electrons. Suppose there are 10 atoms per meter cube. And the number of free electrons is also 10. 10 free electrons per meter cube. This is true because one atom will give me one free electron. Copper atom, in the outermost shell, there is one free electron. So one atom will give me one free electron. So n copper atoms will be n free electrons. So number density of electron is same as number density of copper atoms. Is that clear? Any doubts? Unmute your mic and ask your doubt. So Tarun, did you understand?
Sir, I got disconnected, sir.
Yeah. So what I want to say is this formula, did you hear what I say? Current is VNA. This is the drift velocity, and E is the electron charge, N is number density of electrons, and A is the cross-section area of the conductor. Okay, so this formula can be proved. This derivation, you know. Tarun. Unmute your mic.
Yes, sir, the derivation kind of makes sense.
Yeah, so the way to remember this formula is remember this one V now. Okay, one E is silent. Okay, this V is drift velocity. This number density is number of bits of free electrons. So for a copper atom, once the density is known, I can find the number of copper atoms per unit volume. Because mass of each copper atom I know, and this mass of the copper material. So from this I can find the number of copper atoms per meter cube, and capital N is same as number of free electrons per unit volume. Why is this true? Capital N is number of copper atoms per unit volume, and N is number of free electrons per unit volume. Why are these equal? So meeting will get
actually how, sir? Because
yeah.
free electrons in the sense it should be in the valence, right?
So basically one copper atom will have one outermost valence electron. So one copper atom will give me one free electron. So two copper atoms will be two free electrons. So n copper atoms will be n free electrons. So number density of copper atoms and number density of free electrons are same. Okay.
Okay, sir.
So rejoin the meeting again. It will get cut now. So this also there is an example here. So this is the relation of the current and the drift velocity. Delta T will cancel on both the sides. Okay.